In this video, we'll further our discussion of line integrals through conservative vector fields. So we're finding work of this vector field. First thing we need to show is that it is conservative. So the partial of n with respect to y. I don't know if you recall this from previous notes a while back, but we actually can break this into two different terms like this. That's just 0. When it comes, I'm doing the wrong here. This should be x. When it comes to x, that's going to go to 0. But this one's just going to go to 1 over 1 plus y squared. It's kind of nice. Because that's the constant in front of x. All right? So we have that. We also need the partial of m with respect to y. The x is gone. Inverse tan gets me exactly what we need. Therefore, f is conservative. All right, that allows me to use the method. So I'm looking for this phi that's going to give me f when I take its gradient. So I can rewrite my vector field as the partial of m with respect to x. I'm lied, it's not m, it's phi. Partial of phi with respect to x, and then partial of phi with respect to y. And that's equal to our m n. So we can work backwards. Then phi of xy is just the integral of phi, partial of phi with respect to x dx. That's how we got there. So that's the integral of m dx. I'm going to go ahead and plug m in there. It's x plus tangent. And before you freak out with the inverse tan, it's in terms of y. That makes our life much easier for the moment. So this xy grabs a y, and then also this tangent grabs a y, plus h of y. This should have been an x. Okay, forgive me. Go back. All right, this is dx. I think I got so obsessed with the y and the inverse tan that I distracted myself. Okay, the integral of x is 1/2 x squared. And then this is just tagging x on that inverse tan. Sorry for that total tangent there. Wrong way, too. And this is h of y. There we go. All right, so I like to write it down again, just like every time I do one of these. I have a very predictable pattern that I'm doing every time. I know exactly how I'm going to write it. Okay, 1/2 x squared plus x tangent negative 1y plus h of y. So I'm going to take the derivative then. So d of phi with respect to y. The only thing that's going to stick is that inverse tan to give me a 1 plus y squared underneath the x. The x is a constant. H prime of y. And this is going to be equal to n. Well, we just rewrote n just a second ago. We can do that same thing here. And that's really going to help us out. So we know h prime of y, because that x over 1 plus y squared is gone, is just equal to y plus 1 over y squared. To keep things short, this is just a u sub. So I'm just going to do the u sub for us. You can stop and work it out if you like. It's just an integral. With the u sub of our denominator, we end up with 1/2 ln 1 plus y squared plus c. Just to keep videos, I know there's quite a bit. We're getting towards the end of our course. We have that. So, with that, I like to rewrite my phi of xy. I think we have the function. We have 1/2 x squared plus x inverse tan of y plus 1/2 ln of 1 plus y squared plus c. All right, now we have our potential function. Then we can find work. Work is the line integral over the conservative vector field dotted with dr. And that's just phi of 1, 1, which is the point B that they gave us. And then the initial point was 0, 0. Just to help us out in calculation, you just plug 1 in. It actually isn't that bad if you look through it. It's if you know your inverse tan of 1, which is just radical 2 over 2. So this ends up being 1/2, 1 plus radical 2 plus ln of 2. All right, so that's work in that conservative vector field. Again, I want to point out that this path didn't matter which way we took. We just went from one point to the other. At no point did we even mention the path besides the initial point and the final point.